Okay, so this is the higher tier question 4. So since 2017, new bimodal electric diesel trains, so bimodal simply means they run on electric and diesel, by two, have been introduced to run between Swansea and London. A velocity time graph for one of these trains is shown below. Now, this question was a little confusing perhaps due to the lack of units, but I think that's deliberate, so you have to talk in general terms. So if we refer to our knowledge organizer for this, so we can see here we've got a panel in the knowledge organizer about what to look for in a velocity time graph. Okay, so if the train is stationary, then we would expect to see a zero velocity over a period of time. If it's got a constant speed, then obviously it's going to be a higher line up the velocity axis, but horizontal. Accelerating, it's a positive correlation, and decelerating, it's a negative correlation. It also says that to calculate the distance travelled using one of these velocity time graphs, we'll have to have a look over here now because this is a more detailed treatment of velocity time graphs, that we look for the area under the line of the graph. Okay, so we can apply a little bit of our maths GCSE and we can work out the area under the line of a graph of various shapes we might see on the question. So if we go back to the question now, so the question says use information from page 2 to compare the distance travelled and accelerations for the parts of the journey labelled AB, BC, CD and DA. So page 2 is obviously our formula page. Okay, so on our formula page it tells us that acceleration is a change in velocity divided by time. Also it's the gradient of velocity time graph, and the distance travelled is area under a velocity time graph. So all those three bits of information there may come in handy to answer this question. So it's always a good idea to look back at the formula page if you're not sure. So if we break this journey down into the various parts, A, B, B, C, C, D and D, E. So between points A and B, if we remember back to our knowledge organizer, we'll remember that this shows constant velocity. Okay, and it says a constant velocity of 4 units, whatever these units are, we don't know what they are, but it's moving at a constant velocity of 4 units. So between A and B, train moves at 4 units. We can't determine what they are for a period of 1 unit. Again, we're not sure these might be hours, minutes, seconds, we don't know what they are, but the fact that there's one of them there, so it shows that it moves at this velocity of 4 for a period of time of 1. Okay, but now we need to calculate the distance that it travelled, because we've commented there on the velocity. Okay, we've not said that there's no acceleration or deceleration, perhaps we should. So no acceleration, okay, because the line is horizontal. The distance travelled is the area under this part of the graph. Okay, so it's a rectangle with sides of 1 and 4. So the train travels 4 units, because 1 times 4 is 4. And we don't know what the units are, so we'll just call them units. Okay, so in some ways it makes our life a little easier. Now, between B and C, if we briefly refer back, we can see that the train is decelerating, it's getting slower. Okay, so between B and C, the train decelerates. To calculate the deceleration, we might need to use one of the equations we saw earlier. Okay, so on this we know the velocities, and we know the velocity at the start of the journey, the velocity at the end of the journey, and we know how long it takes. Okay, so if we just remind ourselves from the velocity graphs. We could use the gradient if we're feeling mathematical, or we could use this one, change in velocity divided by time. Okay, so what do I mean by that? Well, the change in velocity starts off at 4 units and it goes down to 0 units. So it's changed by 4 units and the time is 1 unit. Okay, so 4 divided by 1 is 4. Okay, however, because it's a deceleration, it's a good idea to put that in as a 0. Okay, so it decelerates at 4 divided by 1, which equals minus 4 units of deceleration. Okay, again, we're not sure what they are because we've not been given them, so we'll just call them units, and comes to rest. Okay, so comes to rest is a physics term, meaning it's not moving anymore. Okay, because it's got a velocity of 0. And that covers the deceleration. What it doesn't tell us is the distance travelled. Okay, so the distance travelled now, we can treat this as a triangle. And from your maths lessons, you know that the area of a triangle is half base times height. Okay, so the base is 1 and the height is 4. Okay, so 1 times 4 is 4, and half of that is 2. Okay, so it travels 2 units of distance, which if you ever look at this shape compared to that shape, makes a lot of sense, because this shape here, that shape there, is half the area of that shape there. And we've previously calculated that this area is 4. Okay, so that's 4 and that's 2, right? So the train covers 2 units of distance. Okay, so 2 units because of half base times height. Okay, and between C and D, the train is stationary for 3 units. Okay, so it comes to rest and it stops for 3 units. So obviously if it's stationary, it doesn't cover any distance, and there is no area under the graph to calculate, so we don't need to comment on that. And then between D and E, we can probably work out without even looking at the graphs, the knowledge organizer, etc., that it accelerates. Okay, so D to E accelerates. And again, if we use the idea that acceleration is the change in velocity divided by the time, so the change in velocity, well, it starts at 0 and it goes back up to 4 again. Okay, so the change in velocity is 4. This time it's a positive value because it's accelerating, and that happens over 2 units of time. Okay, so the acceleration is 4 divided by 2. Okay, so that's 4 units of velocity divided by 2 units of time, which gives us 2. Okay, so the acceleration is 2 there. So it accelerates at 4 over 2, which equals 2, positive 2 units for 2 units of time. And then the distance travelled, again, we can apply the half base times height formula. This time, though, it's a wider triangle, so it's 4 times 2, which is 8, divided by 2, because that's what half is 4. So it accelerates at 4. No, the half base, I'm talking rubbish here. So base is 2, the height is 4, that's 8. Divided by 2 is 4. Okay, so the distance travelled is half base times height, just to know what we're talking about, which is half of 2 times 4. Okay, so 2 times 4 is 8, and half of that is 4, so that would be 4 units there. Okay, now this is a QER question, so ideally this would be written out in a lot more sentence form, but really because there's so much information to impart, then it's quite difficult to do that. So I would hope that the examiner would be able to accept an answer like that. That's a bit more sort of mathematical. Okay, moving on, because this is quite a big question. We've now got the diagram, or the picture rather, of our bimodal train. Okay, so this shows a 5-carriage bimodal diesel electric train, because it's a train and it's got 5 carriages. And the table below shows information about 2 types of bimodal electric diesel trains. So basically, this row is about a 5-carriage train, this one, and this one is about a 9-carriage train. So we add on another 4 carriages in between the glass carriage and the engine unit there. Now, if you look at this information, not surprisingly, the mass of the 2 trains is significantly different. Okay, it's not quite double the mass because it's only a 9-carriage train, not a 10-carriage train. Okay, the maximum speed is the same because each of these individual train carriages have got the motors to push it along and the brakes and all the other bits and pieces. So the maximum speed is the same. The acceleration is the same, okay, because again, each of the carriages has got its own motors and therefore can bring the train up to speed at the same rate. The standard deceleration, so this is braking, is the same, and the emergency deceleration is the same. Okay, so the only thing that differs about these 2 trains is the mass. Right, so for a journey from Swansea to London, 2 of the 5-carriage trains are joined, making a 10-carriage train. The 10-carriage train has the same speed and acceleration as a 5-carriage train, and indeed a 9-carriage train. Okay, so state Newton's second law of motion as an equation. Okay, so Newton's second law of motion as an equation is simply force is mass times acceleration. So that is Newton's second law there. And we need to apply this to the question. So use information from the table to answer the following questions. Use an equation from page 2 to calculate the resultant force needed to accelerate the 10-carriage train. Now, quite why it's referring to page 2 when it's just asked us to write it down there is a bit of a mystery, but let's just double check that it is available to us on page 2. Okay, so where are we now? It's on here somewhere. Oh, here we are, sorry. Resultant force is mass times acceleration. That's put off by the word resultant there, which looks remarkably like F equals ma. Okay, so we're going to use this. So what we need to calculate this, we want to accelerate, we want to calculate a force. In fact, I should have seen the resultant force there. That would have given me a clue there. So that the resultant force, I'm just going to call it F, is the mass times the acceleration. So the mass we're talking about here is the mass of 2 5-carriage trains. Okay, so we've got the mass of 1 5-carriage train there. So it's 2.3 times 10 to the 5 kilograms times 2. Okay, because there are 2 of them to make up the 10-carriage train. And then we're going to multiply that by the acceleration. Okay, and it tells us in here, in the question rather, that it tells us that it's basically the same. The acceleration is the same regardless. So the standard acceleration for this train on the table is 0.7. So it is for 5, it is for 9. We can assume it is for 10 as well. Okay, so times 0.7. And I've not put the units in here, okay, for simplicity, but the answer to that is 3.22 times 10 to the 5 newtons. Okay, so they give you the units and the answer there. Okay, now this question, a little bit more difficult possibly. It asks us to use the equation acceleration is change in velocity divided by time to calculate the time taken to accelerate the 10-carriage train from rest to its maximum speed. Now, the reason this I think is, I feel is a little more difficult is we want to calculate the time, okay? And yet the equation we're given is given for acceleration. So we need to rearrange this equation. Okay, so this is always a good time to introduce a formula triangle. So if we turn that into a triangle, okay, so acceleration and time will be on the bottom, and change in velocity, delta t, is at the top there. Actually, delta v rather than delta t. Delta v. And in order to use this equation, we need to ask ourselves, well, what do we want to know? We want to know the time taken. So if we cover up time taken, so time is going to be delta v over acceleration. Okay, that's how triangles work. So delta v, the change in velocity, so this is from rest to its maximum speed. So rest is 0 meters per second, and the maximum speed is 55.8. So delta v, the change in velocity, is 55.8. Take away nothing, which is 55.8, and then the acceleration is 0.7. Okay, so the calculation we need to do is that acceleration is 55.8 meters per second divided by 0.7 meters per second squared. Okay, and if you calculate that out, you get 79.7 seconds. Okay, so a little over 10 seconds over a minute. Oh, 20 seconds over a minute, sorry. So a minute and 20 seconds to get to full speed, which makes sense because trains don't tear off the train track. Okay, so they take a while to get up to speed, but still, for such a big vehicle, that's pretty impressive. Okay, and then the final question. A student states that the 9-carriage train is approximately double the mass of the 5-carriage train, and if they were both travelling at the same speed, it will take approximately double the time to stop in an emergency. Explain whether the two claims made by the student are correct. Okay, so his first claim is correct, okay, because if we look back at the question, the mass of the 9-carriage train is 4.4 times 10 to the 5 kilograms. We didn't actually calculate it out here, so perhaps we should do that now. But the oh, no, I just realised. Didn't finish that off there. It's 2.3. Okay. So 2.3 times 2. Okay, so 2.3 times 2 is 4.6 times 10 to the 5. Okay, kilograms. So 4.6 and 4.4 are similar. They're not too far away. Okay. Because he does say approximately in his statement, approximately double. All right, so 4.4 times 10 to the 5 kilograms is approximately the same. If that's even a phrase, approximately 4.6 times 10 to the 5 kilograms. So his first statement is correct because they're not entirely dissimilar. However, his second statement, we need to refer back to the table. He's saying that a train that's double the mass will take double the time. Okay, but as we established before, the deceleration of these two trains, 5 and 9, are the same due to the fact that all the carriages have brakes, and we can pretty much assume that the deceleration of the 10-carriage train is also going to be 1 meter per second squared. Okay, so it will slow down at the same rate. So so the second statement, or second claim, is incorrect, as the table states a common deceleration. Okay, so it doesn't seem to matter how heavy the train is, they will decelerate at the same rate due to the fact that every single carriage has brakes. Okay, right, so that was the end. It was a bit of an epic, that one.